The second part of this lecture on separating proteins will cover high-performance liquid chromatography, abbreviated HPLC. You've probably heard about HPLC already, so this will be a little bit of rehearsal. However, please be aware that the separation of macromolecules like proteins follows somewhat different principles, so it is worthwhile to look at the liquid chromatography again in this context. This simple slide shows the setup of the instrumentation. In order to do high-performance liquid chromatography with small particle-size stationary phases, you need a pump to generate pressure. I detail this also here because you will also do this during the practical part of the course. If you would like to see a little bit more about the lab and the practical parts, see the video below by Jan Willem Mainz. The next part is the injector, again to introduce the sample. The column is the centerpiece of the HPLC system. This is where the separation takes place, where molecules distributing between a stationary and a mobile phase. As a detector, in this case we usually have light absorption UV detector. In other cases, as you've already heard, you may have a mass spectrometer. Unfortunately, this is not possible within the course of the practicum. At the end, you can have a fraction collector to collect the molecules that you've separated. You will do this also in the practicum, because you will do subsequent analyses on these molecules to identify the proteins. Let's look at two principal features of chromatography. First, it's the adsorption isotherm, here given according to Langmuir. What does it show? It shows the concentration of a molecule, in our case this would be a protein, in the mobile phase, that means it's injected from your sample, and the concentration in the stationary phase. The steeper the isotherm, the higher the affinity of the molecule for the stationary phase, and the stronger its retention. Generally, macromolecules have many binding sites, so they have a very strong affinity for stationary phases. It is rather, as shown in this slide, the high affinity binding. So how can I get them off the column again? For proteins and also for peptides, it is compulsory to use a gradient for elution. For example, you bind the molecules when they have a high affinity for the stationary phase, and then you may add salt or an organic modifier depending on the stationary phase gradually the gradient mixer, somewhat similar to what you've seen for the gradient gel, making an immobilized pH gradient, and slowly decrease the affinity until we reach the low affinity binding region and the protein will elute from the column. B is a measure in the Langmuir adsorption isotherm to describe the affinity of a molecule for stationary phase under a given set of mobile phase conditions. It is called an isotherm, as it's in the name, because these measurements are done under constant temperature, since temperature obviously also has an effect on retention. So what makes HPLC so different from liquid chromatography? In fact, most of the separations to date are HPLC separations. This is an electron micrograph from the early 90s, when HPLC was still something special. As you can see, you have a highly regular set of silica particles, all of about 1.5 micrometer diameter, packed together in the densest packing density. You also see that sometimes there are defaults of smaller particles. So the heart of HPLC is to synthesize such regularly shaped spherical particles of all the same diameter. This will allow you to make a very dense packing and to have very good mass transfer between the mobile molecules in the mobile phase and in the stationary phase. So the small particles are the secret to high-performance liquid chromatography. How does the small particle diameter translate into high performance? Let's revert back to the well-known Van Deemter curve, which you've already heard about before. The Van Deemter curve gives the relation between separation efficiency and flow rate, because high-performance liquid chromatography does not only mean high separation efficiency, but also high separation efficiency in a short time, meaning at a fairly high flow rate. We do not speak really about the volumetric flow rate here, but rather the linear flow. That means the millimeter per second that the mobile phase travels through the column. HETP stands for height equivalent to a theoretical plate. A theoretical plate is a term coming from distillation. Each theoretical plate in a distillation column means that there is one equilibrium established. The smaller the height equivalent to a theoretical plate, the higher the efficiency. As you can see from the column, there are a couple of contributors that decrease the efficiency of a chromatographic column. First of all, the A term, tortuous flow term. This is simply related to the quality of column packing. You can imagine if a column is not well packed and there are void spaces in between, or if the particles are not very regular and cannot be packed very densely, then you will have remixing of molecules that were already separated. You may even get turbulent flow areas which lead to remixing of molecules. This will degrade the separation. As you can see, the A term is pretty much independent of the flow rate. The B term is related to the diffusion of molecules. As you know, diffusion occurs if there is a concentration gradient. Naturally, if you want to separate molecule, you will have a concentration gradient between them, because molecules will be concentrated in certain areas of the column. However, if you would stop the flow there, then molecules would diffuse out, and after a certain time the concentration would be everywhere the same. This happens if the flow rate is very low. Molecules have a lot of time to diffuse, and the HETP gets bigger, so the efficiency decreases due to that. C is the most important term for HPLC. It's the mass transfer kinetics term. That means how fast can molecules exchange between the mobile phase and the stationary phase. The smaller the particles, the faster the mass transfer kinetics. This is at the heart of HPLC, of the more recently developed ultra-high performance HPLC, UHPLC. So you can see the mass transfer term C is strongly dependent on the flow rate. It gets bigger and bigger the higher the flow rate. That means simply the less time the molecules have to transfer between the mobile and the stationary phase. Very high efficiency packing materials used to date have a very shallow C term. That means the flow rate can be increased without decreasing the efficiency significantly. The Van Diemter curve has one important feature, which is a minimum. This minimum is the highest efficiency of the column, or the smallest height equivalent to a theoretical plate. This is the optimal flow rate for the column to be used at. Let's look at a few of the principal means of separating proteins and peptides chromatographically. First, a widely used approach is ion exchange chromatography. Remember, we already talked about ion exchange during the chapter on solid phase extraction. It's the same principle here. A protein may be positively charged at a given pH, and if you use a negatively charged stationary phase, there will be ionic or electrostatic interaction between the positive and negative charges, so binding of the protein will occur. This binding can be broken with the gradient of increasing salt concentrations such as sodium chloride, or by change in pH, so that the protein will become negatively charged. It can be also vice versa. We will look into this into more detail later on. The second mode is size exclusion chromatography. Here proteins are separated based on their size. This reminds somewhat of SDS page. However, the separation is inversed. The large proteins come out first out of the column, and the small proteins last. Why is that so? The particles that I showed a few slides earlier are not solid. They contain pores. Pores on the order of tenths of nanometers. This is roughly the size of a protein, considering also its hydration layer. So size exclusion chromatography separates based on the hydrodynamic volume of the protein. This can be different for two proteins of the same molecular weight. One protein may be long, like a spaghetti, and another one of the same molecular weight might be round like a ball. The round protein thus appears smaller to the size exclusion column than the long protein, despite the fact that they both have the same molecular weight. The proteins that have trouble getting into the pores will just flow around the beads and come out first. Proteins that can access the internal volume of the beads, which is considerable, will take a much longer path and will be delayed. They will come out later from the column. Size exclusion chromatography is performed without a gradient under isocratic conditions. There's a wide range of affinity chromatography materials for proteins. Not the least, many different immunoaffinity materials where antibodies against the given protein are immobilized. These antibodies can capture the protein, retain it, and you can wash away all the other proteins. You can then elute by changing, for example, to an acidic pH from the immunoaffinity column, enriching your protein considerably. There are many other, less sophisticated and less specific affinity reagents. So this is a very large field in protein separation, especially in research. Last not least, we have reversed phase chromatography. It's not really a good protein separation method, it's rather used for peptides and small proteins. Why is that so? Reversed phase chromatography works with organic solvents and a very hydrophobic stationary phase. Under these conditions, proteins may unfold, or denature as we call it, and even precipitate. So this renders the method of reversed phase chromatography not so suitable for protein separation, although new materials have been developed that are not quite as harsh. Proteins often lose their biological activity during reversed phase chromatography. So this is not really a method to obtain biologically active proteins. Ion exchange chromatography, as explained before, seems rather straightforward, but there are some additional considerations that you need to take into account for proteins. In principle, ion exchange chromatography separates proteins with differences in charge. And obviously, this charge is dependent on the pH value of the mobile phase. The separation is based on reversible interaction between a charged protein and an oppositely charged chromatographic medium or stationary phase. The elution is performed by increasing the salt concentration or changing the pH, as explained before. An important feature of ion exchange chromatography is that it can concentrate proteins very well. This is very important for preparative protein isolation, for example, for the purification of biopharmaceuticals. Biopharmaceuticals are often produced in cells in culture in a highly dilute form, something like a milligram per liter. You would like to have them concentrated so as not to have to handle large volumes. Imagine a big bioreactor for a biopharmaceutical may be as large as multiple tens of thousands of liters. So ion exchange chromatography is often used as the first step in the so-called downstream processing of biopharmaceuticals. There are two classes of ion exchange chromatography materials: anion exchange, where negatively charged proteins compete with negatively charged mobile phase ions for the positive groups coupled on the column, and cation exchange chromatography, where it is the other way around. Remember also a chapter on solid phase extraction. You can have weak and strong cation exchangers and weak and strong anion exchangers. In case you do not remember what that means, please refer back to the chapter on sample preparation. Here's a scheme of a cation exchange chromatogram. First, the column is equilibrated to be at the proper ionic strength and pH. Then the sample is applied, preferably in a solution and buffer that is close to the pH of the mobile phase and similar in ionic strength. Then gradient elution is performed, for example by adding sodium chloride to the mobile phase. At the end, the column is washed to remove tightly bound material, especially when working with biological samples, and then the column is re-equilibrated to start a second injection. When you look at the chromatogram, you will always see unbound molecules eluting right in the flow-through, as we call it, before the gradient begins. These are molecules that may be neutrals or molecules that may be excluded from binding to the stationary phase, as they may have the same charge. They come out right away in the void. Then you see a couple of proteins coming out as peaks, and the gradient here runs for about 10 to 20 column volumes. We do not speak here about time, although we could, but it is easier to speak about, or more appropriate to speak about, column volumes, because different size columns require different gradients and possibly also different flow rates. With biological material you always have tightly bound proteins or other molecules that need to be removed from the column to avoid fouling. If this is not the case, your column will accumulate these molecules and over time performance will deteriorate. Referring back to isoelectric focusing, we would expect this from an ion exchange chromatogram. On the left side we see the realm of cation exchange at lower pH than the pi of the protein, and on the right side the realm of anion exchange, where the protein is charged negatively at a pH above its isoelectric point. If we look at two theoretical curves for two proteins, proteins can have different number of charges, so the retention time RT may be different. However, we would expect that at the isoelectric point none of the two proteins would be retained. However, this is not the case, and the reason for this is that proteins are macromolecules. If we look at the same structure again that I already showed during the talk on isoelectric focusing, you can see that charges are not evenly distributed across the protein surface. You have a highly negatively charged acidic region that is painted in red, and you have basic amino acids shown in blue. So let's imagine that this protein is exposed to an anion exchanger, which itself is charged positively. So then even at the isoelectric point, where the number of blue and red might be equal, the protein will turn around and bind with its red side to the, let's say, positively charged, or you could say blue, stationary phase. If at the same time I offer a cation exchanger to the protein, which is itself negatively charged, then the protein would turn around and bind with its more bluish surface to the cation exchanger. So at the same pH you can expect binding of proteins to both cation and anion exchangers. So the situation is not as simple as with isoelectric focusing. On this slide we see a more realistic picture of what really happens. The protein conalbumin from chicken egg white is shown in retention by ion exchange HPLC. As you can see, its isoelectric point is 6.3, and at this isoelectric point conalbumin binds to anion and cation exchangers. The reason for this is the charge distribution on conalbumin. You can see that it takes more than 1 pH unit below the isoelectric point to avoid any binding to an anion exchanger, and it takes almost 1 pH unit above the isoelectric point in pH to avoid the binding to the cation exchanger. This is a peculiarity of macromolecules that have three-dimensional structure and an uneven charge distribution on the surface. Size exclusion chromatography comes in different flavors depending on who is using it. This has led to a little bit of a confusion of names. In the protein world, we usually speak about size exclusion or gel filtration chromatography, while in the polymer world, gel permeation chromatography is more widely used, since it's often used in non-aqueous solvent systems. However, the principle is always the same. In our case, size exclusion chromatography separates proteins with differences in molecular size, or better to say hydrodynamic volume. Columns are packed with particles containing pores of a well-defined size. Retention is dependent on the penetration of the solutes in the pores, which is proportional to the hydrodynamic volumes. Very importantly, there should be no selective or any interaction with the stationary phase, which is very hard to achieve for proteins, as proteins have so many functional groups: hydrophobic, basic, acidic, hydrogen donor and hydrogen bond acceptors. So it's very difficult to prevent any interaction, but let's say interaction should be minimal so as not to disturb the pure size exclusion chromatography mechanism. The technique is frequently used for buffer exchange on a preparative scale. This is quite logical because buffer ions are small and proteins are big. So it's very easy to separate the proteins from the buffer ions and to replace the buffer with another kind of buffer. This is often done in the so-called polishing final step of downstream processing of biotherapeutics, because the mobile phase composition is rarely compatible with injection into humans. So the protein is obtained in a buffer that is not compatible with injection, and this buffer needs to be exchanged, for example, against physiological PBS. Here you see a typical gel filtration elution profile. On the left side you see a scanning electron micrograph of a gel filtration material. It contains pores through which the proteins will have to migrate to get to the end of the column. If a protein is too big to get into these pores, it will migrate around the particle and thus elute first. Proteins or molecules that can enter the pores will have to pass a longer way through the column and thus elute later. This is shown on the right in a typical elution profile. As you can see, following the injection, high molecular weight molecules elute first in the excluded V0 volume. Intermediate or proteins and molecules of intermediate molecular weight elute within one column volume. According to their size, bigger molecules elute earlier than smaller molecules. Finally, low molecular weight compounds like salts elute at the end of the chromatogram. Each elution of a protein is characterized by a typical elution volume VE. The molecular weight of proteins or other polymers can be estimated by size exclusion chromatography by relating the logarithm to the base of 10 of the molecular weight to the ratio between the elution volume of the protein and the volume of a totally excluded compound. As you can see here, for molecules of similar shape, that means similar hydrodynamic volume, this gives a linear relationship. So if you calibrate your column with standards, then you can estimate the molecular weight of the molecule in question. Please keep in mind, though, that the molecules should have a similar shape, which is a considerable restriction, as few proteins really have very comparable shapes. Some proteins may be called globular proteins, so you can calibrate the column with globular proteins, while other molecules maybe have more an extended structure. In that case, you would have to calibrate the same column with standards of an extended structure. So it's important to remember that we're not really measuring molecular weight with a size exclusion column, but rather the hydrodynamic volume of the molecule. The term affinity chromatography comprises a wide range of chromatographic methods to enrich or separate proteins. Usually affinity chromatography is a kind of ligand binding assay with an immobilized ligand that shows a high selectivity to the protein of interest. It thus separates proteins from other proteins in the biological matrix based on a reversible and specific binding between the protein and the ligand attached to a chromatographic matrix. We'll see more examples later on. Stationary phases can be highly specific. For example, you may immobilize an antibody that recognizes just one protein, or less restrictive, for example by immobilizing the protein concanavalin A that binds to certain structures of carbohydrates on glycoproteins. it thus recognizes a group of proteins that carries these structures. You may desorb the protein from the immobilized ligand by adding a competitive ligand, for example a monosaccharide, into the mobile phase by changing the pH to break binding, at the extreme to denature the protein to break the binding, but you may also change the ionic strength or polarity. What works depends very much on the physicochemical forces that lead to the affinity binding, be they more hydrophobic in nature or more ionic in nature. The applicability is depending obviously on the availability of the required affinity ligand. Some affinity ligands can be tailor-made, like antibodies or other affinity binders obtained by, for example, phage display or other display technologies, while some ligands are chemically synthesized and may recognize a broad range of proteins. These could be, for example, immobilized drug molecules, low molecular weight molecules that bind to certain proteins and exert thus their pharmacological effect. Immobilizing such drug molecules and looking at which proteins they bind has become a very powerful method to look also at off-target effects of such pharmaceutical compounds. Here we see a typical affinity chromatographic separation. As you may remember, it looks very different from the other separations that we've seen. In an affinity chromatographic separation, the column is equilibrated and then a large volume of the sample is applied, usually with the target protein in low concentration in a complex mixture. So most of the material goes into the flow-through, giving rise to this very big peak. This can be X column volumes depending on the volume of the sample that's loaded. Then the column is switched to elution mode with 1 to 2 column volumes in between, and then the proteins of interest are eluted in a very small volume. Affinity chromatography is thus an excellent method to enrich proteins of interest and at the same time to concentrate them. Then the column is regenerated and can be used for the next time, unless the affinity ligand is denatured. Some protein affinity ligands have to be treated with care, so if the elution conditions are too harsh, columns cannot be reused, which may become quite costly. Let's take a look at a few examples of affinity ligands out of a very large range of possible affinity ligands. The first one is a protein. It's a protease inhibitor that binds to the active site of serine proteases such as thrombin, a very important protease in the blood coagulation cascade. By immobilizing a protein, you can enrich and isolate such proteases and at the same time stabilize them, because once they are bound to the inhibitor, they no longer can degrade themselves or other proteins. The second ligand, concanavalin A, was already mentioned. It's a member of the lectin family. These are proteins that recognize carbohydrate structures. In this case, for example, on glycosylated proteins. They can thus enrich a group of proteins that all contain this carbohydrate structure. Heparin is a polysaccharide in itself. Heparin binds to serine protease inhibitors such as antithrombin 3 and can be used to enrich them. Heparin is also a pharmaceutical in itself. By inhibiting antithrombin 3, it can affect the coagulation cascade. Heparin is thus widely used as an anticoagulant. The proteins protein A or protein G recognize immunoglobulins such as monoclonal antibodies. Protein A and protein G are actually from Staphylococcus. They recognize constant regions on the monoglobulins. They are thus excellent tools to enrich antibodies, monoclonals or polyclonal, and thus to study them further. They are often used in the downstream processing of biopharmaceuticals of the monoclonal antibody class. Antibodies themselves can have a wide range of targets. There are thousands of antibodies around against different proteins. Their specificity is sometimes high. Sometimes they also do recognize other proteins, which is called cross-reactivity. It is thus very important to evaluate the specificity of antibodies with respect to target recognition. In recent years, this has been more and more done by identifying all proteins bound to an immobilized antibody by mass spectrometry. Finally, even simple metal ions can be affinity ligands. For example, we saw a trail enrichment on immobilized nickel 2+. Many proteins use calcium 2+ ions as cofactors, so they can be enriched on metal ion containing stationary phases. For example, coagulation factor 8 is a calcium-dependent protein, and it binds to immobilized calcium 2+, which is one step in its purification scheme. As mentioned earlier on, reversed phase chromatography is not really ideal for proteins, but it's pretty good for peptides. However, it's also used for proteins, especially with shorter alkyl chains on the stationary phase. Reversed phase chromatography separates protein solutes based on their hydrophobicity, based on a reversible interaction between the molecule and the hydrophobic surface of the stationary phase. You could also say it's kind of a distribution of the proteins or peptides between the mobile phase and the very hydrophobic stationary phase. It reminds us a little bit of the liquid-liquid extraction we heard upon early on, the distribution of molecules between a hydrophilic aqueous phase and a hydrophobic organic phase. Stationary phases are many. Most of them are based on silica and some on polymers, such as polystyrene or polymetacrylates. They can be derivatized, especially the silicas, with groups ranging from C4 to C8 or C18 or other phases like aromatic rings, as we've already seen for solid phase extraction. Binding is very strong and elution conditions require harsh conditions. The use of organic solvents is mandatory, and often additives are added like trifluoroacetic acid or formic acid. This results in the denaturation of proteins or most proteins unless they are very stable, like insulin, stabilized by disulfide bonds. Thus proteins often lose their biological activity. So while reversed phase chromatography is fine for the characterization of the proteins on a chemical basis, it's usually not suitable for measuring biological activity, or it's not suitable for isolating proteins for further biological studies. What makes the binding of proteins or molecules in general to hydrophobic stationary phases so strong that you need harsh conditions to elute them? This has been described many years ago as the hydrophobic effect. The hydrophobic effect is mainly due to a displacement of water molecules from a hydrophobic surface by a protein or another molecule. Water obviously does not like to be in contact with a hydrophobic surface. This reduces the entropy of the system because water has to be ordered on this surface. If a molecule now comes, like a protein in this case, to take part of the place of the water, then the water molecules that were on this surface before can now freely distribute into solution, thus increasing the entropy of the entire system. An increase in entropy is thus the main driving force for the strong interaction between molecules and hydrophobic stationary phases in an otherwise hydrophilic environment. A reversed phase gradient dilution of proteins looks fairly similar to what we saw for ion exchange chromatography. Columns have to be equilibrated before application of the sample. There are usually unbound molecules that dilute right in the beginning of the gradient, in the so-called flow-through fraction. As the gradient starts, which is usually an increase in acetonitrile or methanol concentration of water-miscible organic solvent, the hydrophobicity of the mobile phase increases. Thus the organic solvent competes with the proteins for the binding sites to the hydrophobic stationary phase. One after the other, proteins elute according to their hydrophobicity, first the least hydrophobic and at the end the most hydrophobic proteins or peptides. As is usual with complex biological samples, there are very hydrophobic molecules, for example phospholipids, that are hard to remove from the column. Here you need a washing step at the end with very high organic solvent, maybe even at elevated temperature, or maybe even switching to a more hydrophobic solvent like isopropanol. It is important to remove all these molecules from the column, as otherwise they would accumulate over time and irreversibly change the column properties. This is generally known as column fouling. Let's briefly summarize the chromatography part. You've learned about the Langmuir adsorption isotherm, describing the distribution of molecules between the mobile and the stationary phase. We discussed briefly again the Van Diemter curve and its relation to chromatographic efficiency, notably the relation between the particle diameter and the mass transfer, term C of the Van Diemter curve. You were introduced to different chromatographic methods and stationary phases for the separation of proteins. Notably, the surface charge and interaction with ion exchangers, anion exchange and cation exchange, somewhat reminiscent of the part-on-solid phase extraction. The relation between the hydrodynamic volume of proteins, or macromolecules in general, and size exclusion chromatography. Mind here that the molecular weight is not always directly proportional to the hydrodynamic volume. Two molecules with different shapes may have the same molecular weight but different hydrodynamic volumes and may thus be separated by size exclusion chromatography. Finally, the hydrophobic effect, which is the driver of reversed phase and hydrophobic interaction chromatography. The hydrophobic effect, which is driven itself by an increase of entropy in the system, makes the interaction between macromolecules and hydrophobic stationary phases very strong, requiring harsh elution conditions. At the end, let's take a brief look at the experiment that you're going to do in the field of protein separation and protein identification. We will use the technique of peptide mass fingerprinting for this, based on multi-TOF mass spectrometry. First, proteins will be separated by HPLC and analyzed by SDS-Page, so you will collect fractions from the HPLC system and analyze the fractions by SDS-Page. You apply chromatographic and electrophoretic methods. To identify the proteins, you will digest them in a gel piece with trypsin, so-called in-gel protein digestion. The peptides that result from this will be analyzed by multi-TOF mass spectrometry to obtain accurate mass measurements. A database will be interrogated with these accurately measured peptide masses to see whether they can be matched to masses in the database and thus can serve to identify the proteins. All this together gives you an example of how proteins can be separated and identified by a combination of chromatography, electrophoresis and mass spectrometry. Let's assume you get a gel like this, and you would like to identify the band at 60,000 Dalton. Okay, in this case we know it is already bovine serum albumin, but it might as well be an unknown protein, as in your case. The next step would be to excise the spot or band that was stained and to wash the gel piece to remove SDS. Since SDS is a strong denaturant, it would denature trypsin or any other protease and thus prevent any digestion afterwards. To liberate different chains and to avoid peptides being linked together by disulfide bonds, you have to reduce the disulfide bonds with a reducing agent and alkylate the free SH groups in the cysteines to prevent them from reforming disulfide bonds at random. Next step is the digestion of the proteins, mostly with trypsin, which cleaves after lysine and arginine. In this way, you obtain the much smaller peptides. These can now be extracted from the gel piece, as they are much smaller and can easily diffuse through the gel pores. and then can be analyzed by matrix-assisted laser desorption ionization mass spectrometry to determine their accurate mass. Let's take a brief look at the reduction-alkylation reaction, which may be new to you. Here we see two peptides that are linked together by disulfide bonds. You could also see two pieces in a protein. The reducing agent used here is dithiothiol or DTT. It contains in itself thiol or SH groups and thus converts the disulfide bond into free SH groups. These groups are not very stable and thus need to be protected in a way by alkylation. Alkylation is often done with an iodide reagent like iodoacetamide. This reacts with the SH group, alkylates them, and thus makes a thioether that can no longer react to form disulfide bonds. In a way you could say it stabilizes the cysteine in the form its iodoacetamide derivative for further analysis. As mentioned before, trypsin is the most favored protease to cleave proteins into peptides at defined sites, but there are other reagents. Trypsin cleaves after lysine and after arginine. In the single letter code, lysine is abbreviated K and arginine is abbreviated R. Trypsin is sometimes contaminated with chymotrypsin, which cleaves after hydrophobic amino acids. This can be a problem because you assume that cleavages only occur after lysine and arginine, but sometimes, as in this case, you may get a cleavage after phenylalanine, abbreviated F. This is not such a big problem anymore, as manufacturers have improved the purification of trypsin, and thus you rarely see chymotryptic cleavages nowadays. Another important cleavage reagent is cyanogen bromide. It's not a protease but a chemical reagent that cleaves after methionine. It is very specific but somewhat toxic, so it's not so popular in its use. However, it can be quite instrumental for analyzing the transmembrane regions of hydrophobic proteins. You can imagine that the hydrophilic basic amino acids lysine and arginine do not occur in transmembrane regions, which are very hydrophobic lipid bilayers. However, you often find methionine in these transmembrane regions, so cyanogen bromide is quite important for the analysis of membrane-bound proteins. About half a microliter of the digest that you'll obtain will be mixed with the concentrated matrix solution as introduced earlier for matrix-assisted laser desorption ionization or MALDI. This generates a so-called peptide mass fingerprint, a fingerprint of your protein based on the accurate molecular weights of the peptides measured by MALDI mass spectrometry. Here is a peptide mass fingerprint of a somewhat larger protein. You can see, even though it's a single protein, this is already a very complex mass spectrum with many measured peptides. You'll thus get a very long list of accurate masses that will have to be entered into the database search. In fact, what the algorithm is going to do is going to compare your masses, the measured masses, with the in silico generated possible masses from all the proteins, for example, in the human sequence database, considering that you've worked with a human sample. If the material was from another organism, you would have to use another sequence database. Please note that we report the masses with 4 digits behind the comma. This is important because accurate mass measurements only make sense if sufficient digits are taken along to really represent the accuracy of the mass measurement. This could be the possible outcome of such a database search. You see different red bars, a green striped area, and red bars on the right. On the y-axis you see the number of hits, from 0 to 10. A hit is a match between the accurate masses that you've measured and a certain number of masses in the database within a certain preset defined mass range. On the x-axis you see the protein score, which essentially is a number for the quality of the match. The higher the score, the higher the statistical significance that this match is a true positive and not a false positive. Matrix Science is one of the companies that started early on, maybe 25 years ago, to develop algorithms for these analyses. There are now more, but Matrix Science and the mascot algorithm is still widely used. By clicking on this link you will get to the Matrix Science URL, and you can enter the data from your analyses in the peptide mass fingerprinting subsection and do the comparison. You will do this during the practicum with instructions from the supervisors. So you will enter your own data and you'll see, hopefully, you'll be able to identify the protein of interest. You may say, why are there 1, 3, 4 hits outside the green striped area, and what is the green striped area? The green striped area represents where you set the threshold for a statistically significant hit. You may, for example, say, my p-value should be smaller than 10 to the minus 3 before I call something statistically significant. This depends very much on the number of comparisons that you make. Remember the biostatistics scores you would have to correct, and this is built in the algorithm, for multiple comparisons, because otherwise you'll end up with a very small p-value, but still with a false positive. That there are multiple hits is not unusual, because the same protein may be in the database in different entries. There may be different forms of the proteins, there may be splice variants of the proteins or proteolytic fragments. We usually call this protein families. So in proteomics, which is this kind of analysis, we often speak about protein families rather than proteins, as proteins rarely occur as single species in vivo. Let's wrap up Chapter 5. You heard about protein separation by electrophoresis. The two main techniques are STS-Page and isoelectric focusing. We alluded to chromatography as a means to separating proteins and peptides. Remember the Langmuir adsorption isotherm, the Van Deemter curve, and the various chromatographic methods and stationary phases at your disposal. Finally, we introduced you to the experiment that you will do during the practicum, which is protein identification by peptide mass fingerprinting, or briefly PMF.